Hello. Welcome to our first topic on querying databases using the SQL query language. We'll also do some recapping of the relational model today because we really want that locked in as we go forward in the course. So here I have what we'll refer to as a table or a relation in our relational databases, which has some number of attributes, which are columns as I have drawn them here, but I'll refer to them as attributes. And then each horizontal slice of this table, what we might normally call a row, but which I'll call a tuple, because that's the more precise term, has the values for a particular entry in our table. And this particular table is of French revolutionaries, so we have a kind of automatically generated ID, a name, a political club, and the year of death for these individuals: Robespierre, Lafayette, Mirabeau, and Talleyrand. And it's worth remembering a few things about the relational model before we start talking about querying it. Remember that we're dealing with set semantics, meaning we have no duplicate tuples. Every tuple in our table has to be unique. And our attributes, I guess one point I should make about this, however, is that when we talk about queries, the result of queries, those are going to use what are called bag semantics, which means they do allow duplicates. So our tables have to have tuples that are all unique, but when we run a query and we get some subset or transform set of tuples out of the table, those may not all be unique. For example, if we extracted the information on the political club from this table, you can see that of course, this would not have all the entries be unique. And so set, unordered, no duplicates; bag, still unordered, but does allow duplicates. The attributes in our table are typed and static. And this means that kind of each of our attributes here has some kind of data type associated with it. So our ID, we might say, is an int. Our name is a string, though in SQL, as we'll see, this is typically written as var_char, so a variable amount of characters up to a maximum of 20 is what we might say the name type is, and club will also just be a var_char, and our year of death would also be an int, but there are others who might have floats. We might have something specifically be a date or a time. That's a type something could have, and so on. And static just means that these are not kind of dynamic values in the sense that they are automatically updating or responding, or are computed, importantly, based on other entries in the table. So we can kind of think about the relational model, these tables, as like spreadsheets with rules. Right? We've talked about some of the rules are type, or a primary key rule that says some attribute has to be unique and not null. So kind of spreadsheet with rules, but something that spreadsheets can do is say, all right, this column is computed based on the values of these other columns, like a formula in Excel, if you've encountered that before. But our relational model tables are static in that kind of every cell just has a set value. It's not computed dynamically based on some combination of other values. The last thing to remember is that our tables are going to be flat, meaning that we're not going to have kind of tables within tables. Like we wouldn't have some table about a political club embedded within this revolutionary table. It would be a separate table with its kind of own flat set of information. And so tables are flat just means we're not kind of nesting them or creating complex structures. We just have some unordered set of tuples. All right. So our main topic for today is the what was originally called the structured English query language, or SQL. This has been around a while. I think originally developed at IBM, and this has been shortened since to just SQL. Still pronounced SQL, but they got rid of the English and threw out the vowels from query. But so we're left with the structured query language. But as you'll see, still maintains this sort of English aspect in that all our operators are not going to be symbols, they're going to be English words. So what do I mean? Let's say that we want to extract from this table the information about the Jacobins, about the individuals who belong to the Jacobin political club. Now, what we could do to write this query in SQL is we would want to select, and you may notice that some of the SQL operators kind of correspond to the relational algebra operators, and in fact relational algebra is kind of what our SQL grew out of. But we're going to select r dot name, comma, r dot id. You may be asking, what is r? Well, so the first part we're saying select, this is what data we want. So we want the name and ID from some table R. Now what is table R? We would say from, we're taking it from the revolutionaries table, but I don't want to write out revolutionaries everywhere in this query to refer to it. I want to refer to it just as R, and so I can actually say revolutionaries as, and then give it some alias, some other name. So now throughout this query, revolutionaries can be referred to as R, so I can say r.name, r.id, and then, so this is just going to select the name and ID of all tuples out of this table. And the last part is the where clause. And this says I want to select these attributes from revolutionaries where it's the case that r.club equals Jacobin. A few syntactic things to note before I forget. These single quotes are deliberate. It differs from between specific databases, but in many cases, strings have to be given in single quotes, not double quotes. And so that's something to keep in mind. And then all queries are terminated with a semicolon. Just to kind of label each row here, this from is where our data is coming from, and this where clause serves to filter our data. So we're filtering it to be just where our club attribute is the string Jacobin. So one other thing is you may have noticed that I have capitalized all the sort of SQL keyword select from, where, and as. This is not a requirement of SQL, and when I kind of type in my own SQL, I typically don't bother because it's sort of annoying to do, but It is convention if you look at kind of any SQL examples online or in the textbook, they will also do this, kind of capitalizing all the SQL keywords. And this just serves to kind of nicely distinguish the SQL keywords from the other parts of the query, but it's not required. And also this is split up onto multiple lines, which is just fine. Kind of everything up until the semicolon is kind of part of the query, and it can be split on to separate lines without any issues. So what would we get as a result of this query? Well, we'd get out the two tuples where the club matches Jacobin. So we get out 1, 2, 3, Robespierre, Jacobin, 1794, and 567, Mirabeau also belonged to Jacobins, but outlived the revolution, survived, did not, was not one of the revolution's children, whom it ate, and died in 1834. All right, and so this query has kind of filtered out two specific tuples that we're interested in. And kind of when we think about what is the meaning of this query, kind of what, how might we kind of think about it in terms of ways that we've interacted with computers in other contexts, and you can think about it as having for each semantics. And I'm using kind of semantics to mean this is the kind of this is the output behavior that you observe. This is not necessarily how the query is actually being executed by the database system. And we'll get into, we'll spend a long time kind of building up the different pieces of how a database actually executes a query. But in terms of kind of an intuition for what these queries are going to do, we're going to have something like for each tuple in R, if tuple.club equals Jacobin, then output, okay, output are tuple dot name tuple dot id. Oh, that is a good point. I simply copied over the tuples into my example output, but that is not what our query did. Our query actually got the name and the ID, forgot the sort of projection part of attributes, so we would actually get out Robespierre, and then the ID, and Mirabeau, and then that ID. So this would actually be the output of our table, not what I had up there before. And so this is sort of the basic form that SQL queries can take. We grab some attributes from some table, do some filtering. There are kind of two other very common kind of core operators that we'll talk about next week when we delve into kind of more advanced SQL, but just to preview them, there's also a way that we can group by some attribute, kind of group tuples together, and then compute like sums or averages or count how many things are in each group, things like that. And then we can also basically have a where clause, some filtering criteria, but applied to aggregates, to like the sum of the elements of some group greater than some amount, and that will be a having clause down here, but group by and having coming next week. For these other parts, select followed by some number of columns. From, we can actually select from multiple tables, and we'll see examples of that, and you'd separate those by commas, just like the columns up are here. And where, we can actually have multiple predicates that we could have club equals Jacobin and some other criteria or some other criterion. We could parenthesize these as well, so you can kind of construct a kind of multi-part predicate Boolean expression in the where clause. So, few other things that SQL can do. In addition to the group by and having that I previewed, if we wanted to, say, order our output according to the year of death, we could have an order by clause here, and then we give the attributes that we're going to use to sort the output tuples. And so we might say, let's order by our .death, our year of death, and let's say that I want, if I order by something, it will by default do it in ascending order. And so we could then say, no, actually we want it in descending order, and that would serve to flip the order of our tuples here, right? Because if we're in descending order, Mirabeau, right, in descending order, Robespierre would come before Mirabeau. Oh, I was saying earlier Mirabeau survived. It's these other two, Society of 89 people. Sorry about that. But Robespierre would come before Mirabeau if we did it descending. If we had left that out, it would flip the order. And note that we can order by an attribute that is not part of our output, because the query has access to the whole table, not necessarily just the attributes that we're including in the output. And so that way we're actually able to order by an attribute that is not displayed here. Another kind of neat little trick is if you want unique, if you only want to output unique unique values, you could do something like this. We could say select club from revolutionaries, and instead of select club, if we said select distinct club, then it would output just unique values of club. It would eliminate any duplicates. And so without this distinct select club from revolutionaries, we'd get Jacobin, Society of 1989 or 1789, Jacobin, Society of 1789, and with distinct, we just get each of them once, because that is what distinct does. So that is definitely useful. And so this is about kind of retrieving data from the database, but how would we kind of manipulate the database in order to insert, say, new tuples into our revolutionaries relation? So let's take a look at that. All right. So first, how would we create a table to begin with? Well, we would say create table. nice kind of English way, English language way of programming a SQL operation, but we want to create table revolutionaries, and then parenthesis, and here we give the attributes and the type those attributes will have for our table. So we would say ID, it's going to be an int, and we're going to have name, and we'll make it a variable, a number of characters, just a variable length string, and French nobles can have very long names, so maybe we'll say 100 characters as a maximum length for that. We then would have club, make that a var char as well. And finally, death would also be an int. And this is a SQL statement that would create a new table called revolutionaries with these 4 attributes that have these 4 types. And again, all of this is case insensitive, but the capitalizing the SQL terms kind of helps them stand out. So how would we insert new data into our table? We've created it. Now we need to kind of insert a new tuple, and we would do that with an insert statement that would insert into, and then what we would need to do is to give the table that we're inserting into, and you can also specify which attribute values you're going to provide. So we could in fact insert a new tuple into our revolutionaries table who didn't belong to any political club, and then that would insert with a value of null for that attribute. And so this insert into, we would say, all right, we're just inserting a tuple with ID and name and nothing else. This is a kind of undying apolitical member of the table who has neither a club nor a date of death. And then after saying the table that we're inserting into, we would say values and then give the ID and name there. If we just want to insert a tuple that has all the values for all the attributes here, we can just leave off the list of attributes. Sort of the default is I'm going to provide all of them. And so let's say that I want to insert something for Danton, noted Jacobin, who, like Robespierre, met his end in 1794 as the radicals lost power. And so this would give us a kind of new tuple with the ID Danton, Jacobin, and 1794 of this insert statement. All right, so that's how, using SQL, we would create a table and then insert things into it. Many database management systems have special functions to create tables out of CSV files or other formats, and various kind of more sophisticated forms of ingesting data. If you go to the web page for the textbook, which is db-book.com. On there, they actually have some SQL that you can download that will create that university database that the textbook uses as a running example, using kind of these SQL create table and insert statements. There's something missing from our create table, however, and that is we haven't told it, we haven't told the database system anything about say which one of these is a primary key, right? We need some attribute that's going to uniquely identify every tuple. And so just sort of looking at our table here, we can say that ID seems like a good candidate for a key. It's unique, has a lot of different possible values. That seems good. Our club, definitely not a candidate for a primary key. It's not going to be sort of a unique identifier for each tuple. Our death attribute, we consider, is this a good candidate for a key? And well, yes, but actually no, because it is kind of unique values here, but we have a potential insert statement that inserts another revolutionary who died the same year as Robespierre, and that would kind of invalidate a primary key constraint on the death year. When we're creating these sort of data models, they need to take into account that the data comes from the real world, and that something like the year of death not going to be unique. All right, but how would we in SQL tell the database which of these things to use as a key? Well, we would just use literally the words primary key, and we can actually do that as part of the line that defines a particular attribute. We just say ID, it's an int, and it is going to be a primary key. And so this will make int our primary key, and off we go. We can actually create as as I may have mentioned, we can have a primary key that consists of multiple elements, multiple attributes, kind of in combination are uniquely identifying each row of a database, of a table rather. And so if we say wanted to use the ID and the name in combination as a unique identifier, what we would change is, instead of having primary key appear on the lines for here, which designate an individual attribute as a primary key, we can actually add at the end of, as we're defining the different attributes, we can say, all right, and we want a primary key that consists of ID and name. And so we can kind of introduce this specific primary key constraint kind of as its own statement and tell it which attributes form the primary key. All right, so we have seen how to query tables, how to create them, how to insert new values. And an important thing about relational databases is that we can have tables that are connected to each other. We can have multiple tables and define relationships between them. So we might have another table in our database, this one called profession, that has information about kind of what pre-revolutionary jobs, say, particular individuals in our revolutionaries table held. And we might, in this table, have two attributes, an ID and a job. And then the entries in this table, we might say, well, ID 123 had the job of lawyer, and ID 567 actually had two jobs, soldier and writer. And so we have these two tables, and they are related. They are kind of contain information about the same entities in our database. And in particular, it's this ID column which links the two these two tables. Now, one important thing to note is that ID, which was a nice, unique primary key over in our revolutionaries table, when we get to profession, ID is not unique, and so we need to use kind of both ID and job together to uniquely identify the tuples in this table. So we'd have the kind of two-part primary key going on there, whereas for revolutionaries, ID will suffice. And it's this relation, which you may remember from the last video, is called a foreign key, where we have an attribute in one table that refers to the primary keys of another table. And so in this case, we have the IDs in our profession table uniquely identify a tuple in our revolutionaries table. And that is what a foreign key means. It needs to be a value that uniquely identifies a tuple in another table. And so our profession table references our revolutionaries table, and with the foreign key of ID, and it's worth considering, well, could this go the other direction? Could ID in revolutionaries reference ID in profession? And that would not follow our definition of a foreign key as an attribute that uniquely identifies a tuple in another table. That say the ID for Mirabeau 567 does not uniquely identify a tuple in our profession table. So kind of the way that these tables are constructed, where we're using this profession table to capture the fact that certain entities have multiple professions, that kind of tells us that, well, all right, profession has a foreign key that references revolutionaries, because that's kind of the direction that the uniqueness goes. So back to SQL, how would we set this up in our structured query language? Well, we have our same create table of revolutionaries, which will say we're just going to have ID as our primary key, and we can do it this way, a little more verbose than just putting primary key after the attribute. And we would also need to create our professions table, and it's going to have an ID that's an int, and this ID, we want it to we want to tell the database that this refers to the primary key in another table. And so to do this, we would say that ID, we would say that it references the revolutionaries table, and in particular it references the ID attribute there. And then we'd also have our job, which we'll again just make variable length string. And so this is how we would create a table that has ID that references some other tables. This is how we would set up a foreign key in SQL. Now, I have not included in this statement kind of something setting up the primary key for this table. And so what would, if I executed this exact code, what would happen would likely depend on which database system I was executing it on. And database system could make different decisions here. It could use all attributes as the primary key. It could create a kind of invisible new attribute that is kind of an automatic counter that just serves as a kind of guaranteed unique key for the tuples here. Or maybe it would give an error and say, you didn't tell me what the primary key was. This is not a valid way to create a table. All right, so to step back and touch on the relational model again, we can see that the relational is just a collection of tables. And we can create them using SQL and give them primary keys and using these kind of foreign keys as a kind of pointer to another table. And something I want to emphasize about this is that this is independent of the physical data. We've been able to talk about tables, the data in them, how to query it, how to create them, how to set up relationships between them without ever having to think about, all right, what are the actual files this data is stored in, how many files, where are they stored, what format are they in, what storage device are they on, anything like that. And so this is all kind of taking place in the logical layer of our database system and kind of illustrates the convenience of this separation of the logical and physical layer that the relational model gives us, and this kind of the basis for the modern era of database systems. All right, so we've seen that foreign keys set up these relationships between tables, but it's joins that actually realize the combinations of data that the foreign key sets up. And we've talked about joins in terms of relational algebra, so let's talk about kind of how they happen in SQL, and this is super important. Joins are kind of the bread and butter of SQL queries, kind of, and there's going to be a homework on SQL posted Friday, and you're going to be using joins all over the place, all over the place. All right. So there's first I wanted to talk about something called an inner join, and this is in contrast to an outer join, which I'll get to at the end. But an inner join is kind of synonymous with join. When someone says, let's join two tables, they almost always mean an inner join. And so usually inner join is kind of not fully written out. And so let's say that we want to get the name and the profession of our revolutionaries. And so our SQL, we know that the data that we want comes after our select, and we want the name of a revolutionary, and we want the job of that revolutionary. And so we're going to have our from, and you see that as I've set up the select statement here, we're going to need a table R and a table P. R needs to have a name, P needs to have a job, and so we're going to select from revolutionaries as R, and we're going to want to join revolutionaries with our profession, and so we can say join revolutionaries as R, join should capitalize as, profession as P, and I now have to tell SQL what it is that I am using to join these two tables together. And so this is where I would say I'm going to join them on R ID equals PID. So this is the expression that I'm using to decide when two tuples are, to filter the output of this join. And so what this query is going to produce is the kind of resulting name of Robespierre and lawyer, and then Mirabeau and soldier, and then Mirabeau and writer. So you're seeing all the tuples in which an ID in revolutionary is matched to an ID in profession, we get the name and the job there. And so for that reason, Mirabeau's ID matched two tuples in the profession table, and so we get two tuples in the output for those kind of name, for when Mirabeau's tuple in revolutionaries was joined with the first tuple in profession, and then it was joined with the second tuple. So just like we thought about kind of in terms of pseudocode, how should we think about these joins actually kind of going through and giving us the output? It would be something like a nested for loop. We're going to kind of loop over one table and then in an inner loop, loop over the other. So something like for T1 in our revolutionaries, and then for T2 in profession, we have our nested for loops, professions. Then we would use our kind of join criteria. If T1.id is T2.id, then that's where we would output T1.name and T2.job. And so if we kind of think about how this would work for these tables, we kind of start off on the first row, Robespierre here, and then in the inner loop, be going over this profession table. So while we're on Robespierre, we're like, first tuple, does it match? Yes, all right, output Robespierre and lawyer. Second, 567 doesn't match. Next, 567 doesn't match. All right, we've finished with the inner table. Go to the next tuple in the outer table, and then go through the inner table again. None of those matched. Next tuple in the outer table, Mirabeau, doesn't match, and then we get two matches. We output those to our query output, and then finish going over the profession table for the last tuple in revolutionaries. And so we get this sort of nested loop semantics for these joins. As I said, this is simply to give us some intuition for how to expect these join queries to work, not necessarily that our database system would use a procedure exactly like this to implement the join. One other note is that the SQL query I've written here is what is called it is making the join explicit by saying we're going to select from this table, join this other table on this criteria. We can write it slightly differently that makes the join implicit, and I find this way kind of more convenient to write out and kind of I don't know, a little more natural. So I wanted to make sure to show you, but we can say select same attributes, name and job, and then in the from clause, we can just give the two tables that we're selecting from separated by a comma. instead of using the join keyword. So we can say from revolutionaries as R, comma, professions as P, and then instead of having this join on, we just use the where clause that we saw at the beginning to give the sort of filtering criteria for how we're doing this join. And so this was our ID is the same as PID. And so these two queries are equivalent, just one is explicit about the join taking place and the other is implicit. And this has this correspondence with what we saw in relational algebra with the join, where we could express a join as a product and then a select on that product. And so here we have something that explicitly does the join, and here we have something that kind of expresses this product. We're selecting kind of these two tables, the product of these two tables where the criteria that we want to join on. So either of those would give us exactly the same result. All right, so a couple fancier bits I want to get to about joins. I said this was an inner join. It's time for an outer join. And so this would be, say, I want the name and the profession of revolutionaries, but I want to include names even when I don't have a corresponding profession in the profession table. And so for that, I would use an outer join. And for this, there is just a keyword, outer join, and there are actually three kinds of outer joins. So our three kinds of outer joins are left, right, and full. So we have left, right, and full outer joins. And I guess let me write this out so that it is clear. So we have left outer join, right outer join, full outer join. And what this says is a left outer join says include all the tuples from the left table, even if they don't appear in the right. So all, I don't want to say rows, I want to say tuples. All the tuples of the left table are included in the output. The right outer join says all tuples of the right table, and the full outer join just says all tuples from both tables are preserved in the output. So what does this actually look like? We have the same r.name and p.job, but we want to include the names even where we don't have an entry for them in profession. And so I'm not going to keep writing out revolutionaries and professions. I'm thinking now it may have been smart to choose shorter table names. So I'll just say rev as R, rev as R, and then we want to say left outer join. We want to left outer join that to our profession table as P. And then we still need to say we want to join it on the ID attribute. And this, in the kind of explicit versus implicit that I showed earlier, that's just when we want an inner join. When we want an outer join, we're going to need to spell it out explicitly that we want an outer join. And this would give us something like we have Robespierre, who was a lawyer, and we would get all the tuples from the left table, right? The left table being we have revolutionaries, left outer join, professions. So revolutionaries is the kind of left of these of the two tables that are being input to the join, whereas professions in this case would be the right. So order matters when we're talking about a left or right outer join. Order that we give the tables to that statement. So we get our so all the tuples of our left table would be preserved. So even though Lafayette doesn't have an entry in our profession table, which really isn't fair to Lafayette, he did many interesting things. We would have that tuple preserved. So because that tuple appears in our left table, it would appear in our output, but it has no p.job. There's no value that exists for the tuple with Lafayette, and so the output would just have null instead of an entry from the professions table. And we'd get this. We'd still get Mirabeau and his two jobs. And then we get Talleyrand, another prolific individual who resorts changing by making it look like he had no job. All right, so this is sometimes it's not nearly as common as our inner joins, but we do have these outer joins too if we want to get an output that has kind of an entry for everything in one or both of our input tables. All right, last kind of problem that we're going to look at how to solve with SQL is what if we wanted to include, or what if we wanted to find all people with two particular jobs? So we want everyone who was both a soldier and a writer in this case. So let's think through how we might attempt this. So first we would kind of think, well, maybe we can join them. Right? Maybe we could join our two tables, do an inner join. We don't need this this outer join, and we'll just say where we'll just say where our job is soldier and our job is writer. So would this work? Unfortunately not, because there is no tuple in the join that has job with two different values. There's a tuple where the job is soldier and a separate tuple in the join where the job is writer. There is no tuple where job is simultaneously soldier and writer. And this is why kind of thinking about this in those for each semantics, kind of nested for loop is useful, because if we're thinking of looping through our tables and nested loops, we can see that no, we're never going to kind of be on a pair of tuples that are getting joined together where this condition would be true. So this is not going to work. So we might say, well, we also need, of course, for this join to work, we still need to tell it that the IDs should be equal. So we might say, well, could we just say it's soldier or writer, and then like parenthesize this so that it gets evaluated correctly. also doesn't do what we want, because what we're looking for is revolutionaries, people who are both soldiers and writers. We're trying to write a query that's going to get us the names of people that have both of these jobs. And if we say or, it's going to give us everyone who's a soldier, as well as everyone who's a writer. And it's not going to limit it to the people that have both of these jobs. So we're going to do something kind of fun, where what we do is we actually do a self-join. We join the profession table with itself. So we're still doing the revolutionaries. We're doing the profession table as P1, and joining the profession table as P2. And for this, we can now say, we can go back to, we want both of these jobs. We're going to say, all right, P1, the job needs to be soldier. P2, the job needs to be writer. And we also have to include in our where clause linking up all these IDs, where our ID is P1.id and our ID equals P2.id. And so we're joining revolutions with the profession table twice. And so remember, join is going to kind of take a tuple and then slap it together with a tuple from some other table. And so we're actually have kind of a triple nested for loop, where we're going over revolutionaries and then over professions, and then inside that over professions again. And where all the IDs match up, then we are joining them together. And then we're looking for the tuples where the first tuple from professions has soldier and the second has writer. And because we're kind of joining this all together and kind of getting all combinations, we will get out and the other, we would need to say P1.job and P2.job to get out the jobs from both of our profession tables. And so we're actually have written a query where it's going to tell us kind of about all pairs of jobs that a person can have. Kind of everyone with multiple jobs, kind of all the pairs will appear from this query, and then we're selecting the ones where we see soldier and writer. So this is, as I hope this illustrates, we can construct kind of quite sophisticated queries using these sort of basic select from and where that we've learned about today, and kind of even a query that seems maybe very simple to express conceptually. People who have both these jobs actually involve kind of a bit of insight into how to use SQL in terms of constructing a query that uses these kind of flat tables that are available in the relational model. All right, we made it. I look forward to your questions and to seeing you in lab on Friday. Ah!